2.6 nth roots of a complex number. Now you can use Demoivre's theorem to solve an equation of the form z to the power of n equals w, where both z and w belong to a set of complex numbers. And this is equivalent to finding the nth roots of w, and that makes sense, doesn't it? To get z by itself, we have to take the nth root of both sides, so we're finding the nth root of w. Now, just as real numbers, x has two square roots, root x and minus root x, any complex number has n distinct n roots. So, if z and w are non-zero complex numbers and n is a positive integer, then the equation z to the power of n equals w has n distinct solutions. And you can find the solutions to z to the power of n equals w using Demoivre's theorem, and by considering the fact that the argument of a complex number is not unique. Now, what does it mean when we talk about the argument of a complex number not being unique? Well, we know that cos of theta plus 2k pi equals cos theta, and we know that sine of theta plus 2k pi is equal to sine theta for integer values of k. In other words, cos and sine repeat every 2 pi radians, and that makes total sense. If we actually show you the graph of sine and cos, the graph of sine is in red, the graph of cos is in blue, you can see they repeat every 2 pi radians. So that's what this statement is talking about. And for any complex number, z equals r lots of cos theta plus I sine theta, so z has been expressed in mod arg form, you can write z equals r lots of cos of theta plus 2k pi plus I sine of theta plus 2k pi, where k is any integer. So all that's happened over here is, since cos theta is equal to cos of theta plus 2k pi, and sine of theta is equal to sine of theta plus 2k pi, we rewrite these results as we see over here. And of course k is an integer. Example number 15, we have to solve the equation z cubed equals 1 for part A, and then for part B we have to represent our solutions to part A on an Argand diagram. So we begin with the z cubed equaling 1, and if you take a look at what we mentioned in the notes, you can see that this equation is of the form z to the power of n equals w, and therefore to solve this equation we'd have to use Demoivre's theorem, and this is equivalent to finding the nth roots of w. What you can see over here, because z is being raised to the power of 3, we'd end up with 3 roots to this equation. Now, I think it will be a good idea, as we're working out this problem, to plot our solutions on an Argand diagram. We have over here a Argand diagram, and if we show the 1 as a complex number, you can see that goes over here, okay? So we've got the 1 over here, and of course if we solve this equation, first of all what we need to do is express z in mod arg form, and what you can see over here, the modulus of z is equal to 1, and that's shown in this diagram here. So now if we know that the modulus is equal to 1, clearly you can see here the argument is equal to 0 because we're lying on the positive real axis. So what we can now do is express z cubed equals 1 in this form over here. So if we do that, you can see we've got 1 times by the cosine of theta plus I sine of theta, where theta is equal to 0. And if we use the result which we mentioned over here, we can rewrite this result. We can rewrite this result as cos of 0 plus 2k pi. So we have 0 plus 2k pi plus I times by the sine of 0 plus 2k pi. And we mentioned why this result makes perfect sense for us, because sine and cos repeat every pi radians. Of course, 0 plus something is just something, so here we've got cos of 2k pi plus I sine of 2k pi. Now, to help us solve this equation, we need to use De Moivre's theorem as stated over here. So how do we go about solving this equation? Well, what we would have to do is cube root both sides. So z is equal to the cube root of 1, which is the same as raising 1 to the power of 1/3. So using De Moivre's theorem, we know that 1 is equal to this result over here for a integer k. So we have cos of 2k pi plus I sine of 2k pi raised to the power of 1/3. And if we use De Moivre's theorem, we have cos of 2k pi over 3 plus I sine of 2k pi over 3. Okay? Now, if you want, you can express this in exponential form. If you were to express this in exponential form, you would have e to the power of I times by 2k pi over 3. Now, different values of k will give different roots, and the question is, which values of k do we choose? So the idea is over here, we need to choose different values of k. Now, happily for us, in the formula book, you can see from the formula book, if we have z to the power of n equals 1, the roots of this equation is given by z equals 2 pi ki over n for k equaling 0, 1, 2, 3, etc. up to n minus 1. So these are the values of k which we need to choose, and we'll take a look at why we choose these specific values later on, but for now, these are the values of k which we'll be using. So, solving this equation, first of all, when k equals 0, you can see here we have z equaling e I to the 0, and that makes complete sense, because when k equals 0, we have I times by 0 over here. So if we put this back into the mod arg form, we have the cosine of 0 plus I sine of 0, which is equal to 1. So this is one root to the equation z1, if we plot this on the Argand diagram, is equal to 1. That's one possible root we can have. So let's just write this down. We've got z1 equals 1. Now let's see what happens when k is equal to 1. z2 will equal e. Now over here, if we take a look at k equaling 1, we've got 2 lots of 1 times pi over 3. So you can see here we've got z equals e to the power of I lots of 2 pi over 3. And if we use the mod argument form, we have cos of 2 pi over 3 plus I sine of 2 pi over 3. So if we work this out, the cosine of 2 pi over 3, that's minus 1/2. And the sine of 2 pi over 3, that's root 3 over 2. So we add on I lots of root 3 over 2. So this is our second root. So if we were to plot this on the Argand diagram, we have something looking like this. Let's just make sure we keep the same radius. So here we've got this line over here. Okay, so this is z2 equals minus 1/2 plus I times by root 3 over 2. And if you want, you can rewrite z1 as 1 plus 0i. We'll just do that just for clarity. Now, the next value of k which we can choose is k equals 2. Okay, but let's see what happens when k equals 2. We've got z3 equals, now if we use what we have over here, we've got e to the power of I, lots of 2 times by 2 times by pi, which is 4 pi, and then we divide this by 3. Now, if we write this in exponential, in a mod arg form, we've got the cosine of 4 pi over 3 plus I sine of 4 pi over 3. Now typically, you can see over here, this argument is not in between minus pi and pi, because 4 pi over 3 is clearly greater than pi. So what we need to do in this situation is subtract off 2 pi. So we've got the cosine of 4 pi over 3 minus 2 pi plus I sine of 4 pi over 3 minus 2 pi. So if we tidy all of this up, you can see we've got the cosine of minus 2 pi over 3 plus I sine of minus 2 pi over 3. Of course, we've got the same answers, but when we express the result in mod arg form, we need to make sure we're in the correct interval. So if we work all of this out, hopefully here you can see z3 is equal to minus 1/2, because that's what the cosine of minus 2 pi over 3 is. Now, the sine of minus 2 pi over 3, that's minus root 3 over 2. So we subtract off I lots of root 3 over 2. So we've got our three equations. Sorry, we've got our three roots to this equation over here. We've got 1 minus 1/2 plus I root 3 over 2, and minus a half minus I root 3 over 2. So if we go back to the diagram over here, let's plot Z3. You can hopefully see here is Z3. Okay? And this is equal to minus 1/2 minus I root 3 over 2. So part B, that's what we've just done over here. Okay? We've just represented our solutions on an argand diagram. Now, what you can see over here, Z1, Z2 and Z3, these points over here lie on a circle with radius 1 unit. And that's because the magnitude of Z1, Z2 and Z3 is equal to 1. So let's just show this circle. So hopefully here you can see we've got the unit circle, okay? Now for part C, we have to show that the 3 cube roots of 1 can be written as 1, omega and omega squared, where 1 plus omega squared is equal to 0. So for part C, so here we've got part A completed, here we had part B completed, part C. The way we can approach this is to let omega equal one of the roots. So we've got this 1 which corresponds to Z1. So let omega equal Z2. So we will let omega equal Z2, which is equal to minus 1/2 plus I times by the square root of 3 over 2. And Z2, if we think about what we had for Z2 over here, if we write this in exponential form, you can see here omega is equal to e to the power of 2 pi I over 3. Now if we work out what omega squared is, because that's in the question, we can see here omega squared will equal this value over here, e to the 2 pi I over 3 squared, which is equal to e to the power of 4 pi I over 3. And you can see over here, e to the 4 pi I over 3, the correct argument for that, as we saw over here, was minus 2 pi over 3. So this result over here is the same as e to the power of minus 2 pi I over 3. And hopefully what you'll notice over here, this is equal to Z3 over here. So if we work out 1 plus omega squared, we have 1 plus omega, which is minus 1/2 plus I root 3 over 2 plus Z3, which is this result over here, minus 1/2 minus I root 3 over 2. And if we add all this together, we get 0. Now, hopefully you can see here, if we take a look at omega and omega squared, you can see these are complex conjugates of one another. So hopefully, let's just make a note. Omega omega squared is equal to the complex conjugate of omega. So that's quite a useful result. Okay. Now, that's this question done. But if we take a further look at this 2 pi over 3, you can see over here the angle between each of these roots on the Argand diagram is 2 pi over 3. And that's quite an important result, and we'll meet more on that later. So in general, the solutions to z to the n equals 1 are z equals cos of 2 pi k over n plus I sine of 2 pi k over n, and if we write this in exponential form, we have e to the power of 2 pi I k over n for k equals 1 to etc. up to n. And in the formula book, the only difference is k starts at 0 and ends at -1, and I showed you that in the example. And the solutions over here are known as the nth roots of unity. Now, if n is a positive integer, then there is an nth root of unity omega equals e to the 2 pi I over n, such that the nth roots of unity are 1 omega omega squared, all the way up to omega to the power of n minus 1. And these over here, the 1, the omega squared, all the way up to the omega to the n minus 1, these form the vertices of a regular n-gon. So it's just a regular shape with n vertices. And if we add all these together, you'll notice here we have a geometric series with common ratio r. First term 1. So if we solve this geometric series by adding all these terms together, we'll get 0. Now this makes complete sense because we've got the first term which is equal to 1, the common ratio which is equal to omega, so the sum of the n terms over here, we've got 1 plus omega squared all the way up to omega to the n minus 1, and here using the geometric series we've got 1, lots of omega to the n, so that's r to the n, minus 1 over r minus 1, so here we've got omega minus 1. So we end up with omega to the n minus 1 over omega minus 1, and because over here omega to the n is equal to 1, so that's using this idea over here, we've got 1 minus 1 over omega minus 1, which is equal to 0. So that's why this result over here works. Example number 16. We have to solve the equation z to the 4 equals 2 plus 2i root 3. Now before we do anything, I think it will be a good idea if we express this result over here in mod arg form. So if we do that, we can do that quite easily on our calculator. So far we've got z to the 4, and if we express this in mod arg form, well, we need to find the modulus and argument. Now on your calculator, if you change the complex settings, so press shift and menu and then scroll down to the complex settings, and if you choose option 2, r is the modulus, theta is the argument, so let's choose that. And if we type in this complex number, 2 plus 2 root 3 I, okay, we get the modulus to be 4 and the argument to be pi over 3. Okay, so we have over here 4 lots of the cosine of pi over 3 plus I times by the sine of pi over 3. Now, if you remember what we said at the start of this video, because cos and sine are periodic, we can rewrite cos theta as cos of theta plus 2k pi, and we can write sine theta as, if I just minimize this, as sine of theta plus 2k pi. So we will be using this idea to help us rewrite this result. So when we do that, we have over here 4 multiplied by the cosine of pi over 3 plus 2k pi plus I times by the sine of pi over 3 plus 2k pi. Okay, and our job over here is to find out what z is, so we need to take the fourth root. In other words, we will raise all of this to the power of 1/4. So z is equal to 4 lots of the cosine of pi over 3 plus 2k pi plus I times by the sine of pi over 3 plus 2k pi. And all of this is being raised to the power of 1/4. So we can now use Demoivre's theorem. We've got 4 to the power of 1/4, and inside this bracket we can multiply the argument over here by a quarter, which is the same of course as dividing by 4. So here we've got the cosine of pi over 3 plus 2k pi over 4 plus I times by the sine of pi over 3 plus 2k pi over 4. Okay, so all I've just done over here is use Demoivre's theorem. 4 to the quarter, well, that's going to be root 2. So over here we have root 2 multiplied by the cosine of pi over 3 plus 2k pi over 4 plus I times by the sine of pi over 3 plus 2k pi over 4. Okay, so we can also write this result in exponential form. We've got root 2 times by e to the power of I lots of pi over 3 plus 2k pi over 4. And our job over here is to choose different values of k to substitute into here. Now, of course, you may remember, if we take a look in the formula book over here at the bottom, we can use a similar idea over here. What essentially we'll be doing is choosing values of k from k equals 0 to k equals n minus 1. And of course n is the power that z is being raised to. So we will start over here at k equals 0 and end with k equals 3, which is 1 less than the 4 over here. So the way we can approach this, when k is equal to 0, we've got our first root, z1. This is equal to root 2 times by e to the I times by something. Now, happily for us, our calculator can actually work out the correct argument over here in between minus pi and pi. Now, how do we do that? Well, if you press shift and the engineering key, we get this button over here. And notice we're in this form over here already. So we've got this root 2, that's the modulus, and for the argument Well, let's type in this and let's change the values of k. So here we've got the pi over 3 plus 2 pi lots of k. K is 0 over here. And then we divide this by 4. So it turns out we get I lots of pi over 12. That's our first root. When k equals 1, z2 is equal to root 2 times pi e to the I something. So let's change over here the 0 to a 1. When we do that, we get 7 pi over 12. So here we've got I times by 7 pi over 12. When k is equal to 2, z3 is equal to root 2 e to the I lots of, so if we work this out, so let's just change this to a 2. We end up with minus 11 over 12 pi. Okay? So, why is this particularly alarming? Well, normally, if we had a third plus 4 all over 4, that's going to be 13 over 12, which isn't in the correct argument between minus pi and pi. So if we use our calculator, that will ensure we end up with the correct arguments. Okay? So I always recommend in your calculator you work out these arguments. And finally, when k is equal to 3, z4, our fourth root, that's equal to root 2 times by e. And if we change this to a 3, we get minus 5 pi over 12. So here we have minus I times by 5 pi over 12. So these are our four roots over here. So therefore, in conclusion, what we end up with is z equals root 2 e to the I pi over 12, root 2 e to the I times by 7 pi over 12, root 2 e to the minus I times by 11 pi over 12, and root 2, just minimize this, times by e to the minus 5 pi over 12 times by I. So these are our four roots. You can also use the exponential form of a complete number when solving equations. Example number 17, we have to solve the equation z cubed plus 4 lots of root 2 plus 4i lots of root 2 equals 0. Now, to approach this question, we want z cubed equals something, because then we can use the methods we've met earlier to help us solve the equation. And that's in line with what we said over here. We have z to the n equals w. We want the equation in this form to help us find the roots of the equation, and we can do that by using de Moivre's theorem. So that's why we want to take this bit to the right hand side. So if we do that, we have z cubed equals minus 4 root 2 minus 4 root 2 I. Now, our next step is to find the modulus and argument of this complex number. So if you go to the calculator, make sure you're in this mode of complex mode, as we saw in the previous example, and just as a reminder on how we do that, we press shift and then go here. We want to change the complex settings to this second one over here. So if we type in this complex number, -4 root 2 minus 4 root 2 I, then you'd find the modulus equal to 8 and the argument is equal to -3/4 pi. So what we will do is write this in mod arg form. So we've got 8 lots of the cosine of -3 pi over 4 plus I times by the sine of -3 pi over 4. And our job is to find out what z is. But before we do anything, we can use the idea which we met previously, recognizing that cos and sine are periodic. We can add 2k pi to this over here. So if we do that, hopefully here you can see we have 8 lots of the cosine of -3 pi over 4 plus 2k pi plus I times by the sine of -3 pi over 4 plus 2k lots of pi. Okay? And what we will now do is cube root both sides. So z will equal the cube root of this entire thing, which is the same as raising something to the power of 1/3. So we have over here 8 lots of the cosine of -3 pi over 4 plus 2k pi plus I times by the sine of -3 pi over 4 plus 2k pi. Okay? And then we will raise this to the power of 1/3. And now if we use Demoivre's theorem, we have 8 to the power of 1/3. And then here we have the cosine of -3 pi over 4 plus 2k pi over 3. And notice multiplying by 1/3 is the same as dividing by 3. And then we add on I times by the sine of -3 pi over 4 plus 2k pi over 3. So we've just used Demoivre's theorem. 8 to the power of 1/3, that's equal to 2. So we have over here 2 lots of the cosine of -3 pi over 4 plus 2k pi over 3 plus I times by the sine of -3 pi over 4 plus 2k pi over 3. Now we can rewrite this result in mod arg form, in exponential form. So here we have 2e to the power of I lots of -3 pi over 4 plus 2k pi over 3. And for us to find the 3 roots of this equation here, we need to choose different values of k. And you may remember from the formula book, so if we just take a look at what the formula book says, we start at k equals 0, we end at k equals n-1. And of course over here, because we've got a z cubed, we will end when k equals 2. So we have over here, when k is equal to 0, we have z1, our first root, which is equal to 2e to the I times by something. Now happily for us, our calculator will already work out everything in the correct form. So if we press 2, which is the modulus, and then press shift and then the engineering key for the angle, we have over here, if we type all of this up, we have minus 3 pi over 4 plus 2 pi lots of k. Now k over here is equal to 0, and then we divide by 3. So you can see over here for the first angle we get over here minus pi I over 4. When k is equal to 1, z2, let's just work this out. So when k equals 1, we get the angle equaling 5 pi over 12. So we get 2e to the I times by 5 pi over 12. And when k equals 2, let's just replace this with a 2. So it turns out we get minus 11 pi over 12 for z3 as the angle. So we get 2e to the minus I times by 11 pi over 12. So therefore, our three roots, we have z equals 2e to the minus I pi over 4, 2e to the I times by 5 pi over 12, and 2e to the minus I times by 11 pi over 12. These are our roots. Okay? And during the course of the video, we did mention that we stop at k equals n minus 1. Now why is that? So if you look over here, we stopped at n minus 1. Well, let's see what happens when over here we have k equals 3. If we have k equals 3, we end up with minus 1/4. So essentially the reason we stop at n minus 1 is because it will eventually go back to the start over here. So that's why we finish at k equals n minus 1.